Okay, welcome back to Giving Shapes to Blobs, Foundations of Point Set Topology. In the previous lesson, you would have learned what a topology is, at least on a finite set. You talked a little bit about blobs and sets, and there were some exercises for you to do. Hopefully you did the exercises. One thing that you would have learned during the exercises, for sure, is that drawing topologies can be pretty hard. There are often a lot of open sets that you need to draw. We'll talk in this lesson about how to more efficiently actually specify a topology. It turns out you don't need to actually draw every open set to specify a topology. But let me just motivate what I'm about to tell you about by telling you actually how hard topologies can be to draw. So it turns out that there's actually a non-discrete topology on 9 points with over 250 open sets. And if you were given this as an exercise, draw this topology, would you want to do it? Should we draw it? I really don't want to do that. And I'm sure you don't want to either. I do like drawing circles and blobs around points, but I don't know if I want to draw 250 of them in a row. So let's not. Okay, so what do we want to do? What do we have to do if we want to specify a topology, but we don't want to draw every open set? Well, something you might have noticed when you were finding all of the topologies, say on 3 points, or if you were trying to do the same thing for 4 points, or even if you were just trying to find there was one of the exercises where you were trying to find a topology which contained some points, but as an open set, but didn't contain another open set. It turned out that you only needed to draw, a couple of actually basic open sets in order to give the whole topology, right? So we'll talk now about which open sets you need to draw, essentially, to give the whole topology. Which open sets should be considered the basic open sets? So let's consider that example with over 250 open sets just for a second. Here's my 9-point space. It's got 1, 2, 3, and then a whole rainbow of dogs. Which open sets do I want to draw if I want the topology to contain over 250 open sets? Well, it turns out that the basic open sets are not nearly as scary as a family. They're just these ones. And I'll explain why this gives a topology in just a second. Okay, so what is a basis for a topology? What should we consider basic open sets? Okay, so if we take a blob, call it X, it's a basis for topology on X is a family B of sets. So B is a collection of sets, a collection of open sets we'll call basic open sets, such that 1, the empty set is a basic open set. The empty set should always be a basic open set. And it should always be an open set, which is why. 2, well, we need to know what to do with every point of X. So every point of X should be in some basic open set. If we don't say what open sets a point is contained in, then we don't know what to do with it, essentially. Okay, condition 3 is a little bit more involved. So condition 3 says that if V and W are basic open sets, so below I have V and W, V is on the left and W is on the right, and you can see they have kind of an I-shaped intersection in the middle. Okay, so if V and W are basic open sets, and P is some point of the intersection of V and W, you can see P is in that I-shaped intersection of V and W. Okay, if we have V and W and a point in their intersection, then there has to be some basic open set in the intersection that contains P. Okay, I repeat. If we have 2 basic open sets, V and W, and P is a point of their intersection, then there has to be a basic open set, Z, say, containing that point P and contained in the intersection of V and W. Okay, so the motivation for all of this is that we want all of the open sets of the topology to be a union, some union of the basic open sets. We want to be able to only take unions of basic open sets to get all the open sets in the topology. let's look at a quick example. So I have this 4-point blob. It's got 4 dots. Those are the points, the 4 points. And I want to specify a topology on this 4-point blob. I know one set that I certainly would like to be open. It's these 3 points on the left, contained in the blue. The blue is to denote an open set. Is this a basis? Am I done yet? Have I specified all the basic open sets I need to? Well, certainly the empty set is kind of implicit. I'm just going to assume the empty set is around. That's fine. It's actually point 2 already that I haven't satisfied yet. I need an open set around every point in the space. Luckily, I have another open set in mind. It's these 3 points on the right. So this actually satisfies the first 2 conditions of basis. Maybe I'll flip back to that for a second. The empty set is as a basic open set, and every point of X is in a basic open set. So far, we're good to go. Is this a basis? Is this a basis for a topology yet? Well, unfortunately not. We have 2 basic open sets. There's the guy on the left and the guy on the right. But in their intersection, there are these 2 points. And there are no basic open sets around those points. Well, luckily, I have some idea of which basic open sets I'd like. And I would like each of these points individually to be in their own open set. So let's throw those in. Okay. So actually, this is a basis for a topology on the 4-point blob. And in order to generate a full topology, I just need to take unions. So taking unions gives me a topology on the 4-point blob. Okay, so you might have wondered at this point whether every topology has a basis, whether or not it suffices to specify any topology by just some basic open sets. And actually, yes, it is possible. In fact, every topology is a basis for itself, but there are often simpler ones. Be missing the point to give every open set as a basic open set. Okay, so let's look at some examples, the 2 extreme examples. I like discrete topologies, personally. They have very nice bases. Every discrete topology has a very nice basis. And basically, you just want to put every point in its own basic open set. That's it. This is a basis for a topology. Now, of course, the empty set is always implicit. Don't worry too much about that. The trivial topology also has a very nice basis. Just one basic open set. It's the whole set. There's not much more to say there. So let's go back to that scary 250 open set topology on 9 points. So every one of the points is in its own basic open set, other than these 2 dogs on the bottom right. They're saying, let's stick together. They want to be in the same open sets. So how many open sets are actually in the topology generated by this basis? Well, it turns out that if we actually think of the 2 dogs in the bottom right as one dog, then taking unions will give every subset on, say, 8 points. I say 8 because I'm considering the bottom 2 as 1 point. Well, as you probably know, 2 to the 8 is 256, which is more than 250 open sets. So I didn't lie to you before. And this is not discrete because every open set containing one of the 2 dogs on the bottom right will contain both of those dogs. So it's not the discrete topology. The discrete topology has more open sets. Okay, so now if you want to understand the basis for a topology concept and actually how to use a basis for a topology, and understand why drawing a basis for a topology is actually almost always easier than drawing the full topology itself, There are some exercises for you to do. I hope you do them. And don't forget to return for lesson 3, in which we look at some more complicated examples of topologies.